마이크. 강연 전에 안내 한 번 더 드릴게요.
Ladies and gentlemen, we'll make an announcement before we begin the special lecture, public lecture. I would like to ask you to take your seat and also silence your mobile phones. And for today's public lecture, we are going to provide you with simultaneous interpretation services. So those of you who are joining offline, please turn to channel 1 for Korean, channel 2 for English on your simultaneous interpretation services receiver. And we have now opened all the online channels, so I believe there are some of you who are joining us online. So on YouTube, through IAU channel or Kaus Foundation, you can also look at the Korean subtitles. The Kaus Foundation channel will also, can you silence your mobile phones? On the Kaus Foundation channel, we are going to be joined by Professor Doeleman, who is also a member of the EHT team. So he will answer some of the questions. So if you want to talk to Dr. Chung as well, please join us on Kaus Foundation channel instead of the IAU channel.
네. 오케이. 네, 이제 본격적.
Ladies and gentlemen, before we begin the public lecture, I would like to ask you one more time. Please silence your mobile phones and all the electronic devices that you may have. And we are providing you with simultaneous interpretation services today. So on the receiver that you have received, please turn to channel 1 for Korean, channel 2 for English. And those of you who are joining us online, as we have announced before, there are two channels, IAU channel and Kaus Foundation channel. On Kaus Foundation channel, you can also talk to Dr. Chung Tae-yeon, who will be answering some of your questions real time. Now, we are going to begin the first public lecture for International Astronomical Union Congress 2022. Nice to meet you all. I'm your MC today. I am Professor Jeong-Hae from Yonsei University. There has been several showers in Busan today, and it was quite humid. But in spite of this difficult day, we are joined by so many people, online and offline. I would like to thank you all very much. This public lecture started on the 2nd of August, and it will continue until next week to celebrate the IAUGA. The theme of this year's IAUGA is Astronomy for All. In line with this slogan, we are trying to open as many opportunities as possible for people to join us. So we have prepared 2 public lectures today and tomorrow in the same location and same time, and also on the same channel on YouTube. So as for the first public lecture of IAUGA, we are joined by Professor Sheperd Doeleman, who is professor of Harvard and Smithsonian. Some time ago, we saw a picture that looked like a ring, and that had sent shockwaves around the world. And it was a picture of black hole that was 55 million light years away. The mass of this black hole was 450 billion times the mass of sun, which is really astronomically huge. In spite of this mass, because of this huge density and long distance, no single telescope on the Earth could resolve this, because this was such a tiny object in the universe. In order to gain image of this black hole, they had to connect multiple radio telescopes in various parts around the world to achieve a Earth-size telescope, and that is what all Event Horizon Telescope is about. Today, Professor Doeleman, who is also the founding director of the Event Horizon Telescope, is going to talk about EHD, and he is leading hundreds of researchers throughout the world, and he has taken a picture of M87 and recently another black hole in our own Milky Way. This image has verified the Einstein's general relativity theory, and it has helped us understand more about how gravity impacts the universe. So we are going to invite Professor Doeleman, and he will tell us how everything about his journey in gaining the image of the black hole. When the presentation is over, we are going to have a Q&A, and we are going to be answering questions from on and offline audience. So this is going to be a great opportunity to have some of our questions resolved. So for today's public lecture, we have 2 interpreters, Professor Lim Jong-Yo and Professor Song Hae-in, who will be simultaneously translating this. Professor Doeleman.
Okay, thank you very much for that lovely introduction, which I understood part of. So I'm here to talk to you today about the Event Horizon Telescope and to tell you a little bit about how we took our first picture of a supermassive black hole. And we started off asking ourselves, could we do this seemingly impossible task? Because black holes, as I think we all know, is when matter is condensed to such a small region of space that the gravitational field is so intense that light cannot escape. So just the thought of trying to take a picture of something that tries with all of its power to be invisible is itself kind of a big challenge. But if we could do this, the prize would be wonderful, right? Because we would get to test Einstein's theory in the one place where it might break down, the edge of a black hole. And more than that, these black holes are responsible for why the night sky looks the way it does. They are fantastically efficient engines for turning gravitational potential energy into radiant light and redistributing matter and energy on galactic scales. So black holes really are why the night sky looks the way it does. So we set off on this quest to image black holes, and I'm going to describe how we did it and some of the results. But before I do, I just want to say 축하합니다. For the Danuerdi satellite, which is an amazing advance. It is launched just yesterday. It will explore the moon in many different wavelengths, and it is really an honor to be here in South Korea on the day that it was launched. So, 축하합니다. So I want to start off by talking about black holes, of course, by referencing Einstein and his theory of gravity. So Einstein said, we have to rethink our concept of gravity. It's actually a deformation in space-time. And within that deformed space-time, matter moves on paths of least distance, or paths of least time, right? So it changed the way we thought about gravity. And overnight, it solved one of the great problems, right? Mercury, the planet closest to the sun, would always move a little bit in its orbit. Its orbit would always precess a little bit in a way that was not explained by the current form of gravity. And general relativity, his new form of gravity, solved this problem. But it also made a very interesting prediction. Einstein said that if you were to look at starlight just grazing the sun, it would be bent by the mass of the sun, in this case by 1/2000th of a degree, a very small amount, but just enough so that we could tell the difference between Newtonian gravity and Einsteinian gravity. And in 1919, Sir Arthur Eddington undertook two quests, so we had one off the coast of Brazil and one to the island of Principe, and they photographed the sun during a solar eclipse. And you can see here, these parallel lines here show the positions of stars that were measured accurately enough that they could tell that Einstein's theory was the right one, that the positions of the stars that were changing were doing it so in just the right way to be in agreement with Einstein's theory. And overnight, Einstein became a household name. This is the front page of the New York Times, November 10th of 1919. Lights all askew in the heavens. Like nobody knew what to make of this. Only a few people, they said, understood why this happened. But it was a fundamental change in how we thought about the universe. And one of the most fundamental changes was discussed by this man, Carl Schwarzschild, just a year after Einstein came with his theory. And he pointed out that if you have a small enough region of space with enough matter in it, there's a region called the event horizon, which is just 2 times Newton's gravitational constant times the mass of the black hole divided by the speed of light squared, just a bunch of constants together. And if you are within that region, you can never escape. So once you go inside, even if you are traveling as fast as the speed of light, you can't get out again. Okay? Now, this was thought to be a mathematical curiosity only. No one thought that these objects could ever be seen or would exist in the universe. But over time, we have come to understand that the universe contains many, many exotic and very strange objects. So first, there are white dwarfs, and these occur when a star like our sun expires. It can no longer resist the force of gravity through the nuclear furnace inside of it, and it can collapse to something the size of the Earth, and it has a density of about 1,000,000 grams per cubic centimeter, very, very dense. Now, if you have a larger star than that, it can collapse to a neutron star. This is even more exotic. This is an object that's the size of Busan, but weighs the same as our sun, or a little bit more. This is extremely dense, right? This is 100 trillion grams per cubic centimeter. Now, if something is even larger than that, a larger star, then it condenses to something, a black hole, right? And it's only defined by the spin and the mass of the black hole. It collapses within the event horizon. No stiffness of matter can resist the force of gravity at that point. Okay? And we have seen some evidence in stellar remnants for these objects, and most recently we heard it with LIGO. LIGO heard two black holes merging and then ringing. So we know that these exist now. Now, if you go to the centers of galaxies, there was a lot of evidence that there were supermassive black holes in the center of these galaxies that weigh millions or billions times what our sun does. This is Hercules A. It's a galaxy that's about 2 billion light years away. And we think in the center of it is a black hole that weighs 4 billion times what our sun does. Now, you're looking at optical light here. This is light from stars. If you put on radio glasses, if you were to look at this in radio light, this is what you would see. You see something extraordinary. You see jets of material leaving from this supermassive black hole on either side, traveling 1.5 million light years across. Now, the only thing that astronomers and physicists think can drive these outflows is a spinning black hole where the magnetic fields around the black hole are twisted, and like an egg beater, you spin eggs, it accelerates particles out as if they were beads on a wire that's turning, and accelerates them to near light speeds from the North and the South Pole. Now, this can be extremely efficient. A nuclear explosion is under 1% efficient. It turns 1% of the matter into an explosion. This can be over 25, even up to 40% efficient. So it's one of the most efficient engines in the entire universe. And this is why we want to study this. We want to zoom in by factors of 100,000 or 1 million to see what is driving these cosmic blowtorches. Now, why do black holes shine? Because you could ask yourself, look, if all the light is being absorbed and it can never escape, why do we see black holes? So in a paradox of their own gravity, black holes are actually some of the brightest objects in the universe. So if you were to take an apple and you were to drop it from this height, you would liberate about 1 joule of energy. Well, how much is that? That will power your cell phone for 1 second. Now, if you took the whole mass of the Earth and you condensed it into a size only about a couple of centimeters across, it would be a black hole. If you then drop the apple from the same distance, it will be moving very close to the speed of light when it hits the center, and it will liberate 10,000 trillion joules. So just redistributing the matter and launching the apple from the same position, you have a huge efficient engine liberating vast quantities of energy, right? So if you drop the apple here, you can now power all of Manhattan for an entire year. So this is why black holes are magic. They're able, just by the force of their geometry around them, to change gravitational potential energy into radiant and luminous light. Now, what does a black hole look like? If you were to zoom in, what do we think it would look like? Well, some of the first work on this was done in the early 20s, and Max von Laue, who's a very famous physicist, said, well, the event horizon here is the cause of the size that we'll see. Okay, so we start with the event horizon, but it's really this point here, the photon orbit. This is the point where light is forced to move around in a circle around the black hole. That really determines how big the black hole will appear on the sky. And Max von Laue traced this back to our observing position, which is over here. And it turns out that this size here is a very peculiar number. It's the square root of 27 times the Schwarzschild radius. That's how big the whole black hole will be. And in 1921, you can see right there at the bottom, he derived this exact number. Now let me make this real for you. What you're going to see is light coming from all around the black hole, because when the black hole attracts matter to it, it heats up to billions of degrees. So there's a very, very hot gas around the black hole, and light is coming at the black hole from all directions. And when you do this, you wind up seeing that the gravity of the black hole bends light. And if you are here in the Earth, you wind up seeing a very clear signature. you see a lot of emission around the black hole with a ring. And that ring is exactly the square root of 27 times the Schwarzschild radius. This presents an amazing opportunity. If we can see this image, we'd be able to test Einstein's theory and this prediction and determine that Einstein's theory holds at the event horizon itself. Okay, so this is the real motivation behind a lot of the Event Horizon Telescope. Now, over many years, people asked themselves what would the black hole look like, and they used very sophisticated computer codes on big clusters of computers to find out what this would wind up looking like, and they even made movies showing that the gas is moving around the black hole, but you always see this circular feature. And this is what the black hole, this is what the Event Horizon Telescope set out to measure. So the first object that we can think of looking at, one of the best cases we have to make for an object that we could actually resolve, is in the center of our own Milky Way galaxy. Now, if you zoom in all the way to the center of the Milky Way galaxy, you wind up seeing these streamers of gas. This is in the radio. So you're looking at an image in radio wavelengths. And all of this matter is streaming into the center here. And this object, that white little dot at the center, almost surely marks the position of a supermassive black hole. And over many years, infrared astronomers traced the motion of stars around an unseen mass. This is amazing stuff. You are seeing stars being tossed around as if they were planets. Something in the center here at this star is so massive that it causes this star here to move in an orbit. And this, as I like to say, if this doesn't knock your socks off, your socks are on too tight. I mean, this is really amazing stuff. And both Reinhard Genzel and Andrea Ghez won the Nobel Prize for this work in 2020. And it is really amazing, amazing stuff. This shows us beyond really a shadow of a doubt that there is something here that weighs 4 million times what our sun does, but you really can't see it too well in the optical, right? So it's a big mystery still. Now, you ask yourself, what wavelength of light do we need to see all the way to the event horizon? So if you wanted to go look at the black hole in the center of our Milky Way galaxy, optical light cannot penetrate all the gas and dust. But also, I told you around the black hole, there's very, very hot gas, hundreds of billions of degree gas. And to see through this gas, you can't use any wavelength. So what I'm showing you here is, this is M87. This is the second best object to look at on the sky. And you see these jets of material that we saw before. And as you zoom in by a factor of 10,000, you still don't know what's at the center. Now, if you want to look at the center, you need to look at a wavelength that can pierce, that can see through all this hot gas. So we start at long wavelengths. And then as you go to shorter and shorter wavelengths, you can see all that hot gas around the black hole becomes transparent. And you're able to see light that's emitted just outside of the event horizon. So all the gas is madly trying to get into the event horizon. It builds up around the edge. And before it goes into the event horizon, it radiates very brightly. And we have the opportunity to map and to see its dynamics and its shape right here. So at 1 millimeter wavelength, we can see all the way to the event horizon. So that's the kind of the magical, optimal wavelength if you want to see a black hole. So now we have to ask ourselves, how big a telescope do we need? So now we know what the wavelength is, but what's the telescope size? Well, it turns out there's a very simple equation that astronomers use. If you want to see something very small, the smallest object you can see is the wavelength of light you're looking at divided by the size of the telescope. Well, we know we have to use 1 millimeter wavelength to see all the way to the event horizon. So it turns out that for Sagittarius A star and for M87, these black holes, we need to see an angle of only 50 micro arc seconds on the sky. That's like seeing an orange on the moon. It's extremely small. So we need a telescope that's 10,000 kilometers across. Now, we can't make a normal telescope 10,000 kilometers across. We could never build something that large. And the way a normal telescope works, of course, is you have a very nice parabolic shape, and light from the black hole bounces off of this parabola and comes to a focus, and that's where you put your camera. So it uses the geometry of the surface of the telescope to focus the light and make sure it all arrives at the same point at the same time. So to make a telescope that's the size of the Earth, we do something a little similar. We take telescopes at different parts of the globe, and we record the data using atomic clocks. So the light that's coming from the black hole, you can think of it as waves, is recorded digitally, and we time tag each of the crests and the troughs with an accuracy that's equivalent to 1 second every 10 million years. These clocks are that accurate. They only lose 1 second every 10 million years. We store all the light on hard drives, just as you would have on your home computer, and we bring them all together to a central location where in a supercomputer, we line up all the recordings, and we replicate in silicon, we replicate in computers what that parabolic dish does with its geometry. We make sure that all the signals arrive and are combined at just the right time to make an Earth-sized telescope. And one pair of telescopes like this gives you one element or one bit of data for the image. Now, even if you had a few telescopes around the globe, that would never be enough. But thankfully, the Earth rotates. So during a night of observing, each pair of telescopes, which gives us one element of the image, fills in on the right here the Earth-sized virtual telescope. So at any one moment, we only have a few red dots, but over the course of the evening, like a spider web, filling out with silvery filaments, you wind up getting an Earth-sized telescope with enough data so you can make an image of what you're looking at, in this case, a supermassive black hole. When I first learned about this technique in graduate school, I thought it was magic. And it has been the wonderful part of my career to realize this technique to image a black hole. But this has always retained a little bit of magic for me. Now, the last piece of the puzzle, now we know what the wavelength is. We know how big the telescope has to be. We know how to build the telescope. The question now is, would nature cooperate? Would nature allow us to see all the way to the black hole? Would there be something there? We had no idea. So we did a very important experiment in 2008, and we used telescopes in Hawaii, in California, and Arizona to see if we could see really compact structure on the scale of the event horizon in Sagittarius A star at the center of the Milky Way galaxy. Now, if Sagittarius A had a finite size, if it was the size of this red dot, then on the short baseline, our resolution is very, very big. We would expect to see all the energy from the black hole, okay? But on the long baselines here, our resolution is so good that we begin to exclude some of the brightness of Sagittarius A star. So we would expect to see a lower amount of energy. And that's exactly what we saw. This is kind of a complicated graph, but I'll explain it. On the y-axis here, you see the amount of energy that a telescope pair sees. And on the x-axis here, you see the distance between the telescopes. And sure enough, on the Arizona to California baseline in the upper left, we see all the energy. And on the longer baselines, we see a much reduced energy, and we can fit a size to this. And in the upper right there, you see that we got a size of 3.7 Schwarzschild radii. This was a really interesting moment. So all of us were looking at these computer screens, realizing that we were seeing something that was only a few Schwarzschild radii across. This was clear indication that not only could we make the measurement, but that nature was also cooperating, that there was going to be something there. We had the hope of seeing the shadow of a black hole. And the next 10 years was spent building out this telescope so that we could go from making a size measurement to making a real image. Now, we also wanted to hedge our bets. We also wanted to get one more source. So we also looked at M87, which is a completely different kind of animal, right? Sagittarius A star is a very timid black hole. It eats very, very slowly, so it's not very luminous. But M87 has this jet that's launching that you've seen before. And we did the same experiment, and again we saw this signature with lower amounts of energy on the long baselines, all the energy on the short baselines, and we were able to make this size too, and this time it was 5.5 Schwarzschild radius. Now we had 2 objects to look at. So we built out the Event Horizon Telescope using all of these sites from around the world. In Hawaii, we have the SMA and the JCMT, 2 telescopes on the summit of Mauna Kea. South Pole, we have the South Pole Telescope. In Chile, we have the ALMA array and the OPEX telescope. In Mexico, we have the LMT. In Arizona, the SMT. And then we also were joined by the IRAM 30 meter in Spain. This was the first time we got all of these sites together. Now, thankfully, everything worked, but it takes a lot of logistics to get this data back to the central facility. One of the interesting things about this technique, called very long baseline interferometry, is that you're effectively freezing the light at each location. Then you bring it to a central location and you play it back, and you line it up with great precision. So this is actually the data that was packed up at the South Pole. It showed up in a FedEx truck at MIT. We unloaded it with a forklift. Can you imagine? We're unloading data. We're unloading light with a forklift. And then we unpacked it, we brought it up to temperature, and finally we were able to process the data. So this shows the whole trip of the data from the remote site back to the central facility. Now, we are not the first people to ship data around like this. So in 1956, this is what 5 megabytes of data looked like. Also unloading huge amounts of data at the time from a truck. So some things changed, some things are the same. The only thing that's really changed here is the units we use to determine how much data we're shipping around by truck. So we first got to look at the data, and I'll tell you this was extremely exciting for us, because when you've been in the field as long as we have, you can recognize very interesting features. So this is the same plot that I showed you before, energy on the y-axis, baseline length on the x-axis. And you can see something very interesting. You can see this, you can see a dip and a bounce. So right away we knew something interesting was there. Because if you try to model this as just a blob, a symmetric blob, you can never fit the data with that curve. Now, if you try to use a filled disk with a hard edge, then you get some bounces, but they're not in the right spot. If you start to look at a ring structure, then the bounces are in the right spot, but it still doesn't fit the data very well because there's some asymmetry. And it's when you start looking at a crescent that you get families of curves that fit everything. So right away we saw that there was something very interesting in the data, that we had the possibility, the hint of a shadow. Now, we don't have all of the data. So you can see here on the left what the Earth-sized virtual telescope looks like. Every place there's a colored line, we have data. Whenever you don't see data, we don't have the data, right? So we only fill in partially the Earth-sized virtual lens. So we use an optimization process, which I'm not going to go into in great detail, but we fit the data, which is the first term on the right, and we also use regularizers. We just ask that the image be positive, that it be smooth a little bit around the edges, but we help the process where we don't know where all the data are. And this shows you how the process converges. It's a very robust, very stable process that winds up giving you the best image with all the data that we have. And you wind up getting a very sharp ring. Okay, so this is the technique that we're using. This was, what I showed you is actually data that was synthetic. We tested this process over and over and over again using test data before we put it on the real data. Then we split up into teams. This is very important. The reason we split up into teams is that we had never imaged a black hole before. And we didn't want all of us to be in the room and everyone to say, we are all seeing a ring. We are all seeing a shadow. We wanted to remove the human bias from this scientific process. So we had teams in Asia, we had teams in Europe, in America, we had mixed teams that combined different institutes together, and nobody could see the data. No one shared their results. Everyone saw the data, and they worked on it independently. They did not talk to each other. And the reason, again, is that it is very difficult to tell the difference between a labradoodle and fried chicken, right? So you can think you're looking at a labradoodle, you can think you're looking at a dog, and you're actually looking at fried chicken, okay? And we didn't want everybody in the room to be convincing themselves of one thing when it was actually something else. And if you think this is hard, chihuahuas and blueberry muffins are really, really difficult to tell apart. So this is why I tell people we had to split up into different teams. Now, on July 24th, we all came together, and all the 4 teams showed us their first images. And this is the moment when we really knew that we had something, because each team, using different techniques, had seen the same ring feature. Okay? So this was the moment when we all celebrated, a small celebration, because we still had a lot of work to do, but here we are in the basement of one of the laboratories at Harvard, where we're sharing this moment together. And this was a great moment of camaraderie across the entire team. Many people combined all of their efforts to make this moment possible. And what you don't see, thanks, what you don't see also is that there are many people on a speakerphone. So it was not just the people here, but it was people from all over the globe sharing in this very, very wonderful moment. Now, then the hard work began, because then we had to try to make that ring go away. Because when you come with a really nice result like this, you have to come with very convincing evidence. So here's what we did. We took these techniques that I told you about, and we trained them on many different shapes. We trained them on rings, we trained them on crescents, we trained them on a filled disk, on doubles, on different morphologies, different shapes. We told them this is what you should be very, very good at. And then when we set them out on the data, they always still found a ring. So even when we trained these techniques to look at other things, they always came back and found this ring shape. So it's a very, very robust result. Now we also think that this is robust because when we looked at other objects, when we looked at quasars, which should have this jet structure, that's exactly what we saw. So this is is a very famous quasar. It's a bright, bright center of a galaxy powered by a supermassive black hole. And you see a core here where the black hole is and a jet being launched by the black hole. So when we didn't expect to see a ring, we didn't see a ring. And when we expected we might see a ring, that's where we saw the ring. So this was very strong evidence, too, that we were on the right track. Another bit of evidence that we had done the right thing is that we had 4 different days of data, each totally independent. So we analyzed each day independently and got the same ring morphology on each day. There are some slight differences here, but the basic ring shape is identical between all of these days. So this also gave us great confidence in our result. Now, to understand why we needed all these antennas, I'll show you the best images that you can make as you add antennas across the globe. If you only have 2 antennas, all you can really do is measure a size, and that's the blob, the symmetric blob you see on the right. If you add an outrigger station in South America to the one in the United States and Mexico, you can see there's something small there, but you can't really make the image. Then if you add an outrigger in Hawaii, you begin to see the hints of this ring. Now you have enough of the Earth-sized virtual lens filled in that you can model the ring. And it's when you add the European site that it really crystallizes. So you need the full global array in order to make this image. And if we're going to make this image better, we need to add more telescopes to the array to give us higher and higher fidelity in our image. Now, what did we measure? So one way of analyzing the data is to just plot a ridge line around this ring. So as it moves around, you wind up recording where the ridge is, and you can measure the size of this ring. Okay? So you wind up getting a diameter, and an uncertainty. Now, this equation up here is just what I showed you before. The angular diameter of this shadow is predicted by Einstein. You see the square root of 27 in there with some constants. And you see m over d, okay? Because we don't know how far away the black hole is, so we're measuring the mass of the black hole divided by the distance to the black hole, okay? But thankfully, we know what the distance is to M87. Okay, so this is all this data I'm talking to you about was on M87, which is 55 million light years away. And you can see the result we got, because we know the distance is 16.8 megaparsecs, so it's about 55 million light years away. And so you read off the mass from this equation, 6.5 billion solar masses. Now this really was a surprising moment for us. Because what you're seeing now is 6.5 million solar masses are within the photon orbit. This clinches really the case for a supermassive black hole in the center of a galaxy. There's only a handful of other possibilities it could be, but really it has to be a supermassive black hole. It's really the only thing it can be reasonably that could be within that small size, bending light around it in this ring. So this was very, very powerful proof of that. So where are we today? On M87, we have a mass here of about 6.5 billion solar masses. It agrees with other measurements that people have made much further out from the black hole, where they measure the orbital motion of stars and the velocity of stars around the black hole. This black hole is circular, so it deviates only a little bit from this circular pattern, which is exactly what we would expect from Einstein's gravity. And you'll notice that the bottom part of the ring is bright, and the top part of the ring is faint. That's because gas is moving around the bottom towards you, and it's Doppler boosted. So it's much brighter where the gas is coming to you. And on the top, it's moving away from you, and so it's dimmer on the top because it's Doppler deboosted. So this shows you that there's light speed orbital motions of the gas around the supermassive black hole, which is entirely consistent with our picture of how gas moves around a black hole. So it's consistent with Einstein at about the 17% level, and we can make that much better with future measurements. And it allows us to study details of the flow around the black hole, and I'll say a few words about that in a moment. So what you should do is you should take your right hand and you point it slightly into the page, and you curve your fingers around. The gas is coming to you from the bottom. So the spin of the black hole is pointing slightly into the page and down, and your fingers trace the motion of the gas. Into the page on the top, out of the page on the bottom, dim on top, bright on the bottom. So for the first time, we've actually been able to see the spin and the orientation of a black hole by using this asymmetry. Now, what you're looking at here are thousands of models that we ran to try to figure out the physics behind what was happening around the black hole. What is the temperature of the gas? What are the magnetic fields in the gas? What does the black hole spin? We tried to fit all of these different models to learn something about how the black hole is eating the gas that's surrounding it. Now, one of the solutions to this came from looking at magnetic fields. So not only did we look at the brightness of the black hole, but we tried and were successful at mapping the magnetic fields. This shows the magnetic field lines moving around the black hole. This is important because, as I showed before, you have this disk of material orbiting the black hole, and a jet is launched from the north and south poles with magnetic fields winding around. Now, in some cases, you get turbulent magnetic fields, which is in the top, and that's called a sane model. And in some cases, you have very, very strong magnetic fields that guide the material into the event horizon, and that's called a MAD model, or a magnetically arrested disk. These are just terms that astronomers use. But they're very important to us because they tell us how the black hole is feeding from the gas around it. And it turned out that because we see these strong ordered magnetic fields, we strongly suspect that this lower model here, this MAD model, is how this black hole is eating. So the Event Horizon Telescope has not only tested Einstein's theory, but it's also telling us how black holes turn this gravitational potential energy from infalling matter into radiant light with great precision. Now, the next object we looked at was Sagittarius star, and it took us a lot longer to come with this image than for M87. And the reason is, there's a couple of reasons for this. One is that there's scattering within the Milky Way galaxy. The Milky Way galaxy is a disk, and we're on the edge of the disk, and we're seeing through all the ionized gas between us and the galactic center, and it causes the image to be blurred. So on the left, you'll see 3 millimeter wavelength. In the middle, you'll see 1.3 millimeter wavelength, where we observe with the EHT. And on the right, you'll see even a shorter wavelength, where we hope to observe in the future. The scattering completely destroys the shadow on the left. You can begin to see the shadow at 1.3 millimeters because the scattering affects short wavelengths much more lightly than it does long wavelengths. And by the time you get to 0.8 millimeters, you can still see the intrinsic structure. So this is why we have to go to very short wavelengths to see the Milky Way black hole, known as Sagittarius A star. Now, the other reason that Sagittarius star was harder is because it changes every few minutes. It's only 4 million solar masses, so the time it takes light to orbit around it is only about half an hour or so. Well, actually, a little bit shorter than that, only a few minutes. Matter orbits every half an hour. So it changes its appearance during the course of a night. So it's very difficult to find out what its structure is because it's changing while you're trying to measure it. So in this case, for Sagittarius A star, we did the same process that we used before. We used many, many different groups, many, many different algorithms, and we came with many, many different images. And as before, we trained all of the different techniques on different shapes. And they always came usually with the same ring, which I'll show you in a moment. But the idea here is that we had hundreds of thousands, on the lower part here, hundreds of thousands of images made of the data. Now, what winds up happening is that you get many, many different images. Okay, so you get thousands, hundreds of thousands of images, and you can group them into different shapes. So you'll see 4 main groupings that we looked at. 3 of them give you a clear ring. And the size of the ring is very, very robust. But the distribution of brightness around the ring changes. That we have no control over, but we can look at the ring size. And there's one on the right there where only a few images show up, where there are 2 bright spots, but not much of a ring. And it turns out that over 98% of all the images that we made have this clear ring structure. So we think it's very, very robust. But this shows you the kind of techniques that we used and the approach we used to make sure that this ring shape that we saw for the black hole at the center of our Milky Way galaxy was very robust and very repeatable. So for Sag A star, which is the second black hole, we have a mass of 4 million solar masses. We know the black hole mass, in this case, with great precision, because the work of Reinhard Genzel and André Agues tell us exactly what the mass should be, and this matches it perfectly. So not only are we agreeing with Einstein, but we also agree with decades of infrared astronomy that looks at the orbits of stars around the supermassive black hole. And now we have 2 sources that differ in mass by over a factor of 1,000 that corroborate and verify Einstein's theories at the event horizon. This is the best evidence that we have for the existence of supermassive black holes in our galaxy, but also in a distant galaxy. So now I want to turn, for the last part of my talk, I want to turn to the question of what comes next. Because whenever I talk about this, the first question is, okay, what are you doing now to improve the instrument? And the answer is we're working on something called the next generation Event Horizon Telescope. All the blue points you see here are where we have existing telescopes as part of the array. The red dots are areas where we could build new telescopes or site new telescopes to increase the filling of our Earth-sized virtual telescope. And so one of the first things you do is you ask, where are all the high points around the globe? because we want to be above water vapor. It turns out water vapor absorbs radio wavelengths. So we want to be as high up as we can. So you see there are wonderful places, in Asia and the west coast of the US, the midline of the Rocky Mountains, the Andes Mountains, even in Greenland, even in Africa. There are a number of places we could extend this to make it truly a global array. Now, the first phase that we're looking at is going to build on what we already have. So this is the current array, and this is the filling of the Earth-sized virtual lens in the bottom that we can achieve now. Now, after the first phase, where we're going to add 5 new sites and increase the frequency, we begin to fill out the Earth-sized virtual telescope so we can make much better images. And by about 7 years from now, we hope to have another 11 sites, which fills everything out to the point where we can make extremely high fidelity images. So what's the improvement? What you see here on the left is an image of the black hole from M87 with the jet. Now, this is really interesting because this is going to allow us to study how energy flows from the black hole down through the jet. And we can't do that yet because we don't have the capability of imaging the jet. But on the right, you see what we can do with the next generation Event Horizon Telescope. We can image the black hole and the jet. But the best part is that we can make movies. The left shows the evolution of this jet. And on the right shows what we can do if we image twice a week. Twice a week, we take a picture and we stitch those together to make a time-lapse movie. And for the first time, we'll be able to show the flow of energy from the event horizon all the way through these jets, really study how black holes change the way the night sky looks to us. Now, for Sagittarius A star, it's moving while we're trying to make an image, but we'll have enough snapshot capability from moment to moment. We'll be able to make images and tie them together into real movies. And on the left, you see a model, and on the right shows what we can do with the next generation EHT. Now, why is this important? It turns out that the size of the shadow of the black hole, the lensing of light around the event horizon, is insensitive to the spin of the black hole. If a black hole is not spinning, it looks about 5.2 times the Schwarzschild radius. If it is spinning maximally, it shrinks only a little bit by about 4 or 5%. So you can't really tell if the black hole is spinning just by looking at the shadow. But by looking at the orbital period of matter around the black hole, that's extremely sensitive to spin. So these movies will allow us to unlock the spin of the black hole and the mass at the same time, enabling us to study these objects with much, much greater precision. Now, the other thing we want to do is, in addition to building the ground array, is moving to space. I mean, we have a telescope as large as the planet now. Who would not want a telescope bigger than our planet? So what you see here in the upper part is how fast, oops, let me go back. Yeah, so what you see in the top is how slow you build up the Earth-sized telescope when the Earth is rotating. And on the bottom, you'll see how fast we can build it when you have satellites orbiting the Earth. Well, it goes very, very quickly. It fills in the entire array, so you can make much better movies and much higher fidelity images when you have space-based platforms. Now, on the right, you see what happens when you put a telescope all the way at the second Lagrange point. This is 1.5 million kilometers from the Earth. If we were to put a telescope all the way out there, we'd have a telescope that's millions of kilometers across, and we'd be able to measure the size of black holes all across the universe. Tens of thousands of black holes would come into range. So either putting a satellite close to the Earth or one far away will give us dramatic improvements in how we study these supermassive black holes. So to summarize, the next generation EHT, by building new sites on the ground, will give us the middle movie. And if we were to put a telescope in geosynchronous orbit, just at about it would give us an improvement of about 3.5 times in resolution. We'd be able to make the movie on the right. So this is what we're thinking about right now, building out on the ground, but also looking to space to make a very, very large telescope. So now I want to talk about the team. When we first started out with the Event Horizon Telescope, there were only a few of us. And we made those first measurements of the black hole size. And as the saying goes, if you want to go fast, go alone. But if you want to go far, go together. And the only way we could do this is building an international team. And this is one of our meetings that we had in Hilo, Hawaii, just before the pandemic hit. And you can see that we're happy, and we're all together, and we're doing what scientists do, which is collaborate in person. And we now have, at the time we had 200 members, but now we have over 300 members from 60 institutes, 20 countries and regions. And the important thing to realize, especially for this audience where there are some students here, is that the early career people, the students, made significant contributions. And I would go so far as to say that if we didn't have all the talented early career people that were involved in this project, we never would have made it to the finish line. It was really the young people that provided a lot of the creativity and the work to get this done. So it was very much a team effort on this final push. Now there is a human dimension to this. So we had a press conference for the M87 result on April 10th of 2019. And we were actually shocked to come down the next day to see this image on the front page of all major newspapers around the globe, as you see. After a few years, I've come to understand that this is because of a few basic reasons. One is, when you tell people you're going to image a black hole, it seems impossible. I mean, how can you take a picture of something that, by its definition, tries to be unseen? So there was this impossible nature of the challenge. The second thing is that it was really scientifically compelling. Scientists from around the world really wanted to understand what a black hole looked like and be able to study a black hole on horizon scales with an image. It also required resources from around the globe. No one group could do it by themselves. We had to come together. So we drew expertise and talented individuals from all around the globe. And that allowed us, this is the fourth reason, to nimbly step around borders. So we were able to work around all the things that normally divide us as people and focus on what united us with this common scientific vision. And I think that whole package, the impact of the science, the mythical status of black holes, and the fact that we did it as a team, resonates with all of us, with the public, with scientists, and it was really a joy to work with this team to pull this together. I think that's why people resonate with this result. I also like to think about what Einstein would think of all this, because we imagine all the time that Einstein is almost with us in the room. And this is really what pushed us to be so careful, because when you have Einstein virtually looking over your shoulder, or you have Schwarzschild or Stephen Hawking virtually with you in the room, you really want to get it right, because this is really a handshake across 100 years. We're really working with, in some sense, these early pioneers. The equations they write down are with us every day. And we owe it to them and to this whole tradition of the scientific process to get it right. But even so, Einstein did all of his work over 100 years ago on this, right? So I think sometimes in my mind what it would be like to go have a conversation with Einstein and to have him realize that the work that he did actually has meaning today. So of course we need Einstein's equations to use GPS. If you don't make relativistic corrections that Einstein came with, your GPS will be off by kilometers. So if we were to go back and talk to Einstein, we'd say, Professor Einstein, 100 years from now, we will use your equations, and you'll be able to tell where you are using your phone that talks to a constellation of satellites. And he'd be very excited, but he would say, what's a phone, right? Because we've come so far from 1919, from 1915, that it took 100 years for this basic fundamental science result to come and make GPS possible. So basic science it always pays off. You never know when it's going to pay off, but it's always a good bet, and it's always a good investment. And the last thing I'll say is a couple of odd photographs. The first is an X-ray. This is the first picture of an X-ray made by Röntgen in 1895. And this is the picture of a flea drawn by hand by Robert Hooke in 1665. In some sense, the HT is part of this tradition, making the invisible visible. On the left, you saw the skeleton inside of a living human body, something that was not thought to be possible. On the right, you see the wonderful world of the very small that's all around us, but is invisible to our eyes. And the black hole image from the EHT, we humbly suggest, is also a new frontier, where we're seeing something that we didn't think was possible, and we think it is a wonderful path for a human endeavor in the future. So thank you very much. I'm looking forward to answering questions.
네, 시작.
So let's start. Thank you for the wonderful presentation, Professor Doeleman. From the image of a black hole, you have talked about what kind of information we can gather and how the telescopes work together and what a big team effort has gone into to gain such an image. Thank you very much for that presentation. Many people have already given us a question. This is the list of questions but I believe people in the audience might also have a lot of questions. So Professor Doeleman, I believe you started from the east side of the US to come here, right? Eastern United States to be here. So it must be morning in the US just when you're waking up. But we have so many questions. So are you ready to stay overnight to answer the questions?
I'll stay here as long as it takes.
네, 뭐 청중들 여기 많이
So I believe the audience should also have a opportunity to ask questions. So those of you who have already given us a question, please don't feel shy. We have microphones on two sides of the room, so we'll receive questions from the audience first. So any questions? Yes, you can come forward to the microphone. You seem kind of shy, but...
Any question is a good question.
안녕하세요, 교수님.
Good evening, Dr. Doeleman. I'm Park Eun-young from Kyung University Astrophysics Department. Dr. Doeleman, thank you very much for the wonderful presentation or lecture. My question is, towards the end of your presentation, you talked about space EHT and expanding the scale of EHP by adding more telescopes. But in the existing projects, you have collected the information from multiple telescopes on hard disk, and you physically brought them to one place. But for space EHT, that's going to be more difficult because wireless internet speed is not as fast you would like to do it. That's why you used hard disk to move the data. So for space EHT, what kind of solution do you have to bring all the data together?
So thank you. That's a wonderful question. And we have spent a lot of time thinking about exactly this issue. So it turns out that we think that we will use lasers and optical communication, not microwave or internet. We'll use lasers, and it looks as though we can reach the data rates that we want to from a satellite to get all the data back. So we will not send hard disks back, but we will beam the data back using lasers. Now, we're still a few years away from realizing the whole system, but we see a path forward on that. So it is indeed a big challenge, and we think we can meet it.
네, 답변 감사합니다.
Thank you very much for the answer.
네, 다음 질문
Next question. Yes, please use microphone. If you have question, please line up right next to the microphone. What about the question not related to your lecture? Will that be okay?
I am at your disposal.
네, 저기 한 분이 나와 계시.
Yes. Would you like to go ahead and ask question? I love black hole. I'm not a scientist. I'm just a general public. As you proceed this project, what was the most difficult thing? What was the greatest challenge that you have faced?
Oh, wow, what a wonderful question. I think that the biggest, probably the biggest challenge was building the team. You know, it's very difficult to focus many people on one project, but it is very important, especially today. We have so many global problems facing us as people. Food, the pandemic, all the things that we need to face as a planet, like climate change. And the only way to do this is going to be to build global teams that are guided by a common vision. And so I take great hope from the Event Horizon Telescope that we can apply some of the lessons we learned to build the team for other big problems that we face in humanity. But that was the hardest thing, to convince people that this was scientifically worthwhile, to convince people to commit resources, to convince existing facilities to work with us, and then to sustain the effort beyond the data taking to make the images. And thankfully we had wonderful team members that made it all possible. But that was probably the hardest thing, building a team, keeping them together, and then pushing it through to success.
Professor Doeleman, whenever I watched your lecture, I've dreamed of meeting you, and it's a great pleasure to see you in Korea. Thank you for coming all the way. Professor Doeleman, do you see the line there? So you can't go home tonight.
Okay, I'm here.
네, 그 다음 분.
Good evening. I'm from Seoul, and I came all the way to Busan just to listen to your lecture today. My dream is to become an astrophysicist like you. And doctor, what made you an astrophysicist? So how can I prepare myself? What kind of study should I do to be a great astrophysicist like yourself?
So first of all, thank you. But I have my weaknesses. So first of all, of course, study math and physics and get a good understanding. But the one thing that is very difficult to teach is resilience. Because in any project, this one also, you can have failure. And you have to be able to face the failure, to learn from the failure, and then do it again. And so I would say that you need to have patience, and you need to have some inner strength to do this kind of work. I'll give you an example. One of the first experiments I showed there in 2008 confirmed that there was very small structure at the black hole at the center of our Milky Way galaxy. And the first time we did that experiment, we failed because there was a problem technically in one of the telescopes. We had put months of preparation into it and months of data analysis, and only afterwards did we realize the project was doomed from the very beginning. And it was very demoralizing. But we were able to make the experiment even better, learning from that experience, and the next year we went out and repeated it. So that will happen over and over in your career as an astronomer, and so you have to be strong.
네, 너무 좋은 답변 감사드립니다.
Thank you for the great answer. I hope to see you at NASA in the future. Frankly speaking, many people ask the same question. What was the greatest difficulty? How did you overcome that? And the previous boy came all the way to Busan just to ask this question and to hear your lecture. So please give a warm round of applause to that boy again. So next question. So let's go to another microphone. Hello, I'm from Chungnam University. I'm also majoring in astrophysics. Thank you very much for awesome lecture. And here comes my question. Professor, what programming language did you use in doing your research? Because if you look at the astronomic physics, photon or super plus were the language that they have used to process the image. But nowadays, they use Falson as a different computer language, Python. So what computer language did you use to process the image? That's my question.
Okay, it's a very good question. So when I was in graduate school and writing programs, we used C mostly. But now most of the work we do is in Python. And we do some acceleration of Python with GPUs and clusters of computers. So we use messaging protocols like MPI, things like this. But a lot of the wrappers we use right now are Python. So if people want to get into this field, I would strongly recommend using Python with the associated libraries that accelerate it in many, many different ways. So that you can't go wrong these days by using Python.
답변 감사합니다.
Thank you very much.
안녕하세요.
Good evening, Professor Doeleman. I'm also a middle school student. You have talked about camaraderie and teamwork.
하는 과정에서
In collaboration, what do you think is the most important success factor for collaborating with your co-workers?
Oh, okay. This is another wonderful question. It'll only take me about an hour to answer that question. I'll tell you one thing that really worked for us and that I made sure of in this collaboration. In many times in a collaboration, you will have 2 ideas or 3 ideas, and you decide to down select. You decide, well, we're not going to use these 2 ideas, we're going to use this idea. And it makes the people who worked on these other 2 ideas not feel good.
Yeah.
Because they've put so much time and effort into developing something. And we consciously chose not to do that. So in the papers we wrote long papers. And we made sure that all the ideas were used to verify the technique that we actually used to produce the data, but were in the paper. So everybody could see their effort carefully put into either an appendix in the paper or the body of the paper. And I created a term for this. I call it creative tension, right? Because there's tension between all of these different techniques, and it makes the whole result better. Because everybody knows they're being compared across, but there's no danger of down select. And that, I think, helped everyone see the project through to the very end. It was a helpful idea for us.
Oh, thank you. Your lecture was wonderful.
대한민국의
In Korea, middle school students, their future very bright. They are passionate, asking a lot of great questions. So let's go to another microphone. Next question. Good evening, Professor. I'm a high school student, and I do a lot of research. One of many high school students who love astronomers. And since I study different kinds of stars, especially extraterrestrial, and people ask me, why are you doing that? And as you said, in the process of development, there could be some technology developments and things that are impossible could be possible next. And I see the value of astrophysics. So although right now we don't have any practicality, but in the process of developing this, eventually we could use that on our daily lives. So I believe that the value of technology is also important. And what is your take on the value of astrophysics?
Question. I mean, it's not going to surprise you to hear that I think that astrophysics and really the exploration of the universe has great value. If you only work on things that have applicable use, you will really limit your understanding of the universe. Okay, so if you only try to work on things that have an immediate gift back to humanity, then you're doing more engineering, which is great, but you limit yourself. The idea of doing basic research in astrophysics is that you cast a broad net intellectually. You look at many, many different ways to solve problems. You identify different inconsistencies in nature, different problems to solve, different fundamental questions. And that always leads you in new directions. So one of the answers I give to this is that if you really want to help humanity, you look as broadly as you can, and you will always find something new. As I said at the very end of my talk, basic research always pays off. You never know when it will, but it is never a bad investment, right? And I think it is an essential investment, because it's the only way to really learn something new that you don't already know.
Thank you. 러블리한
That was a lovely question and lovely answer as well. The lines are too long, so we cannot continue like that. So some of you who are in the line, if you major in astrophysics or space science, please give up your opportunity for other students.
Juan, and I'd like to speak in English rather than speaking in Korean. Is that okay for you?
I can understand.
Okay, thank you. So I am really impressed by your passion and kind explanation for us. And yeah, my question is, when was the first time that you started to think like, oh, I have to focus on like these supermassive black holes, or was it just by some kind of like suggestion by your professor or something? Or yeah, I wonder that.
Yeah, it's a great question. Like, we all have moments as professional astronomers where we make some decision to pursue something. I was a grad student, and I was working on this technique of making a global array, and the natural progression was to go higher in frequency. But that had a lot of challenges. The atmosphere is harder to see through. The electronics are noisier. The receivers are not as sensitive. The objects are typically fainter. Everything was harder. But the payoff was that you got much higher angular resolution. And for these black holes, we knew that to see through to the event horizon, we needed to go to high frequencies. And so at some point, I just dedicated myself to that project. And it needed, that force. I mean, there were not many people working in that area. And so sometimes in astronomy and other fields, if you go where there's not a lot of people working, then you have the freedom and the time to really make advances. And that was the case here. It was a problem whose time had come, and I just decided to throw myself into it. It's not I'm a human just like anybody else. You see an opportunity and you say, I'm going to see where this goes. And it has been a lot of fun. And by the way, like, I don't care about the lines. We'll be here all night. Like, we'll order out food, right? We can order
Sure.
food? Yeah, we'll order food.
Yeah, we can feed you.
Yeah, no.
오른쪽.
I'm a high school student from Seoul that's taking a gap year. Wow, thank you for your mention about the early career researchers in the field. It really got my heart pounding for the students. Thank you for that. And my question would be, I'm a person who's interested in the bigger cosmological problems, including like dark energy and dark matter. And in regards to your mentions of technological advancements, including like the bigger version of the HT, what do you think this would contribute, and whether like, do you think it would shed light on these bigger issues and kind of show us a solution?
That's a very, very interesting question. So first of all, I suggest that you come tomorrow, because there'll be another talk by Brian Schmidt, who is going to answer all of your questions.
Indeed.
So I think that the EHT, as interesting and as illuminating as it is, cannot answer all questions. It really focuses us on the event horizon, and it can tell us something about the larger scale structure in the universe because of how these jets that launch interact with matter on galactic scales. It is likely not going to shed too much light on dark matter, although there are some ways in which the shape of the shadow can rule out some dark matter particles. So there are some limits now on axions, which are one of the components of dark matter that may contribute to these larger cosmological questions you're talking about, which can now be tested by looking at the orbits of light around the black hole. So there are some ways in which the EHT is informing these larger issues.
Wow, that's really interesting. Thank you.
네, 내일 또 뵐게요.
So I will see you tomorrow too. Good evening. I'm from Taedong High School. My name is Kim Hyun-bin. Professor Doeleman, thank you very much for the wonderful presentation. And as I was listening to your lecture, I began to wonder about verification. You said you had 3 teams, one in Asia, one in Europe, and one in the United States, 3 teams verifying on their own. But if the 3 teams, of course you came up with similar values, but what if there are different values? Is there a possibility? I think there is a possibility that each team comes up with different results. So do you also consider that possibility? Or do you go through these trials and errors and make the presentation only when you're very certain that your verification result is correct?
Yeah, so I think I understand the question. So first of all, there were 4 teams. So you talked about 3 teams, but there were actually 4. So imagine that 1 or 2 of the teams had come with a different result. If that had happened, we would have gone back and tried to find out exactly why there was a discrepancy, and we would never have published until the full collaboration was convinced that the evidence was robust. And if we could not claim that there was a shadow, we would not have claimed there was a shadow, right? So if we got to a situation where there was real disagreement in the collaboration, we would have published, well, these are some results that are possible, and these are some results that are possible, and we have to wait to get more data. That would have been a perfectly fine paper to write, and we would adhere to all the scientific process that's required for that. Now, in this case, the ringing that I showed you in that plot, it was so clear, and the fact that all the different techniques locked onto this image right away, that the result was very robust. It was clear as a bell. We spent a long time trying to make it go away, to make sure that it was there, but there was no question at some point that there was this ring structure. But if there hadn't been, we would not have published, if that kind of answers your question.
감사합니다.
Thank you very much.
네, 오른쪽.
Well, I hope to make contributions to the research of the black hole. I'm middle school students. I'd like to become astrophysicist. The theme of your lecture is supermassive black hole. And not only that, what about the primitive black hole? Is there any possibility of imaging primitive black hole?
Oh, I think you're talking about primordial black holes that came into existence at the beginning of the universe. So that's very interesting. The Event Horizon Telescope can really only look at black holes that are actively feeding right now. So if a black hole were alone somewhere, it would not have a signature, it would not have brightness that we could observe with the Event Horizon Telescope. And that's probably the case with most primordial black holes at this point. We see the black holes now because they're feeding, and the matter, as it approaches the black hole, heats to billions of degrees, and we can see that lensed around the black hole. There are even some black holes that are much larger. They're 20 billion solar masses, 20 billion times the mass of our sun. But for some reason, they are not radio loud. They don't emit radio waves. So those we also cannot study. So there are limits to what we can do with the Event Horizon Telescope. We probably cannot study primordial black holes, even though they are, of course, very, very interesting from a cosmological perspective.
Yeah, I was so glad to be here to see your public lecture, and thank you for your answer. And I have a British accent. I'm so sorry.
Okay, 감사합니다.
네, 왼쪽이요.
네, 안녕하세요.
Dr. Doeleman, I'm very much interested in astronomy. I want to be an astronomer. My question is, you said that there are stars that have much bigger mass than the sun, and they can create a black hole. But EHT has shown us supermassive black hole. How are supermassive black holes formed, and where do they originate from?
Oh, wow, that is a fantastic question. Okay, so that's a wonderful question. So astronomers and physicists still do not know exactly how supermassive black holes form in the center of galaxies, but it is likely that there are seeds, that might be 100 solar masses that start combining from very, very large stars, and they start combining over the course of the life of a galaxy, and that even galaxies, when they merge, that have smaller central black holes in them will then come together, collide, and those black holes will then merge. And in this hierarchical merging over galactic timescales, you wind up building supermassive black holes in the center of most galaxies. So it's a combination, really, of accretion, of the black hole feeding, but also black holes merging over cosmic time that almost ensures that there will be a supermassive black hole in the center of most galaxies. But we don't know precisely how this works.
Thank you. Your lecture was so great. I want to be an astronomer someday.
I cannot recommend that highly enough.
이것만 봐서는 지금 대한민국의 중학생 반이 천문학자가 될 것 같아요. 네, 오른쪽 다시 가겠습니다.
네, 안녕하세요. 저는
I'm very much interested in astronomy. I have not majored in this area. I have a question. You talk about EHT, high performing telescope, is operating in different sites. And then the previous question was about a bigger scale of EHT, bigger than Earth, like a space size telescope. Are you implying that probably we can build EHD someplace at Moon or Mercury or somewhere else, just like a James Webb telescope? Can we launch that and can we exchange the data if this is possible? What kind of expectation do you have? That's my question.
It's a great question. So there are two ways we think of improving the Event Horizon Telescope. One is to build many more sites on the Earth, And then we can image fainter parts of the black hole, so we can image the jet. Another way of improving the Event Horizon Telescope is to launch a satellite. And then you wind up getting an angular resolution that scales as the distance between the Earth and that satellite. So you can start to see much finer features. And that's important because we think that the ring that you are seeing is actually composed of an infinite number of rings. Because there is light that comes from, if the black hole is here, it goes around the black hole to you. There's some light that starts where you are and does a U-turn around the black hole. There's some light that goes many, many times around the black hole and comes to you. And all of these wind up giving you tighter and tighter rings of emission that nest themselves. So what this means is that as you go farther out to space, the telescope formed by the satellite to the Earth can see the finest of these rings. And those fine rings encode the spin and the mass and all the physics around the black hole. So the higher their angular resolution, the more finely we can study these infinite number of rings that are around the black hole. So will this be possible? I think that in about 10 years, we will have a mission to space that will increase the size of the Event Horizon Telescope, where we can begin to study the motion and the path of these photons that circle the black hole many times. I hope that answered the question.
너무
I think she got it.
감사합니다.
Yeah.
Thank you so much. I'm your fan.
저 아직 질문
There are so many people who are waiting to ask a question, but since time is almost up, we'll receive one question from this side, and only those who are already in the line will get to ask questions. And among those who are in the line, if you really think you have a really important question, please stay with us. And that we'll receive one question from this side of the room, and we'll officially close this session. Yes, please go ahead.
My heartbeat rate is 155. Oh my God. So nervous. Yeah.
Don't be nervous. Don't be nervous.
I'm a high school student in Daegu, and I'm interested in black hole. So first, thank you for a great lectures. And my question is that black hole images doesn't show the dark part and middle of black hole like other bright areas. Why we cannot see dark region of black hole? This is my question.
Yeah, that's a great question. So, in fact, that's the question, right? So it turns out that the dark patch is formed because any light ray from our eye that's traced back within that central region goes through the event horizon. Okay, so what that means is that any light coming to us from that direction would never be able to escape from the event horizon. So in 1921, that figure by Max von Laue that I showed, he did this experiment where he started firing photons back to the black hole. And he found that within this dark region, they all hit the black hole like this. Only when you go far enough from the black hole does it go all the way around, so you can begin to see the ring of light. Anything interior would hit the black hole, and that means that you wind up seeing this dark region, because that's where light cannot escape.
Okay, thank you. Today you can make a great experience for me. So thank you, very thank you. I love.
Okay. Thank you very much.
네, 지금 말씀
As I mentioned, unfortunately, the time is limited, so we have to close. Only those who are standing right next to the microphone, you will have the chance to ask questions. There are two how should I say, to conclusion, EHT is great, amazing, awesome. And Korean middle school students are also awesome. That's my conclusion. Once again, there were a lot of professional, difficult stuff given and explained by the professor, and some of you might not be able to understand, but still, I guess EHT is extremely important, as professor has emphasized. Globally, the technology and human resources are collaborating, and the depth and also the width of the achievements is immeasurable. No matter where you work, please keep yourself and remember that cooperation and making a team can make a better and greater future. That's my personal view.
감사합니다.
감사합니다.
감사합니다. I also want to say one last thing. If I failed to acknowledge this before, but I want to thank the IAU for inviting me here to give this amazing lecture. It was such a wonderful experience to speak with you all. The level of energy and excitement here in the audience is really something that I'm not used to. So thank you very much for this wonderful experience.